So we'll continue discussing the program control instructions. We'll talk today about subroutines. Subroutines. Routines are a few lines of codes written to perform some task. It's not a main code, it's a subcode. So if you would like to calculate some function within your main program, you may write few lines in your code to calculate this function. Let's say cosine x. So you write a few lines to calculate cosine x. And if you needed to calculate this function many times in your code, you would copy the few lines you've written and paste them to wherever you need to calculate your cosine x. So this will use a lot of memory, especially if you need to calculate this function many times, 10, 20 times through your code. You will copy and paste these few lines 10, 20 times through your code. And instead of doing so, you write this code once and set it aside, give it a name, and whenever you need to calculate this function, you just call this routine, which is called subroutine, calculate the function, and come back to the main program. When you call a subroutine, you have to pass by the stack memory segment to reserve your return address there. Go to the subroutine, calculate the function you are interested in, get the value of this function, come back to your main routine, but you will again have to pass by the stack memory segment to get the return address to know where you should resume your execution, where you start at after calculating the function through this subroutine. Okay, so it's a very important part. It eases the life of programmers and good to include in any software. It's again, as we said, it's a group, a few instructions which performs some given function. But nothing is gained for free. Yes, you save memory space, but at the expense of time. Okay, because you would have to consume some time in calling the subroutine and in coming back from the subroutine. So this will take additional time, but you will save memory. So it's a trade-off between memory and time, because the instruction call, to execute this instruction, you would have to consume some time, and when you come back from a subroutine through the return instruction, you would again have to consume some time in executing this instruction, but you will save some money, some memory. All right. And a stack is usually used to save your return address in. So in going to a subroutine through the call, you save your return address in the stack, and in coming back from the subroutine, you would again have to get your return address from the stack. The subroutine in 8086, 8088 microprocessor is named a procedure. So a procedure is a group of instructions to perform some task in the terminology of the assembly language of the 8086, 8088 microprocessors. And two basic instructions usually used with the subroutine: call in your main program, and your last instruction in your subroutine is return. You have to instruct the system to go back to the main stream of your code. Good. These instructions are as follow. So the call, meaning you're calling a subroutine, you need to add an operand with the call of the subroutine. This operand tells your system where your subroutine is stored at, what address you should start executing your subroutine. And this is done by either modifying IP if the subroutine is inside the currently active code memory segment, or you modify both your IP and CS if this subroutine is stored into some other code memory segment. Okay, again, when you return, you may return to where you left, or you add an operand to the return. This operand means when you return back to the main code, you don't like to start executing right after your code. You need to start somewhere else, and this is determined by your operand. The number given in the operand should be added to the address in your stack memory segment pointed to by your stack pointer. So you add this number of this operand to the number inside your stack pointer, so it takes you somewhere else in your code away from the instruction right after the call instruction. Okay, and the operands of the call are one of these. So you have a near procedure when the subroutine is written in the current code memory segment, or a far procedure where the subroutine or the procedure is written in a different code memory segment. This is why in near procedure you need only to modify the value inside your IP. This is why the operand could be either a memory pointer to 16 bits or a register, a 16-bit register. But if you need to do some far procedure, your subroutine is not written inside the currently active code memory segment, then your operand should be a memory pointer, and this memory pointer points to 32 bits. Okay, the operands of the return could be none if you would like to resume your execution just right after your call instruction. You go to the instruction just below the call instruction and start resuming execution from there, so you don't need to add an operand to return. But if you want to go somewhere else, an operand should be provided, and this operand is only a displacement of 16 bits. Okay, again, the call instruction gives control of your execution to some subroutine, so it leaves the main program to execute a subroutine. So the control now is passed to the subroutine, and your IP has been modified. So it transfers the flow of the program from the main program to a procedure. Okay, unlike jumps, calls, the called instruction passes by the stack memory segment and saves there either IP for your near procedure or IP and CS for your far procedure. While jump, because it doesn't mean to come back to the flow, to the main program. When you jump and start executing your program from where you jump it at, and it's not intended that you come back to the place at which you jump. All right, so jump just modifies the value of IP or the value for IP and CS. Value for IP, if you jump a short or a near, but for your far jump, you modify IP and CS. You do not save any registers inside your stack memory segment. This is the main big difference between calls and jumps. And again, you have to differentiate between a near call, where you modify all the IP, you store IP inside your stack memory segment, and you place a new IP in your instruction pointer to tell the program where to start your subroutine at. This is a near call. You need only to modify your IP. While in a far call, you need to modify both your IP and CS, and you need to save both your IP and CS inside your stack memory segment. Okay, this is why your near call is a 3 byte long instruction. The second and third bytes are used to modify your IP. And you modify the IP and you store the IP register, the current value of your IP register before you modify it. You store it in your stack memory segment. You push it into the stack. Because IP, the current IP, will tell your system where to start at in coming back from a subroutine. While your far call is a 5 byte long instruction. Bytes 2 and 3 used to modify IP, while byte 4 and 5 used to modify your CS. But before doing this modification, you have to store both IP and CS registers inside your stack. Why? Because they will tell the system where to come back to the main program, where to start at after getting the value needed from your subroutine. Now your return instruction. When you return from a subroutine, you remove from your stack a 16-bit if you're coming from a near return, or 32 bits if you're coming from a far procedure. The 16-bit of the near procedure used to replace the value inside your IP, while your 32 bits are used to change both values inside your IP and CS registers. Because you have now come back to your main program by modifying IP, again if you're coming from a near procedure, or IP and CS if you're coming from a far procedure. This is the normal way, the usual way of returning from a subroutine. But sometimes you provide an operand with the return to modify the value of your stack pointer. So you're going to return to a specified address you know of. And this address is not the address of the instruction right after your call instruction. It's a different address. So you have to give some operand to be added to the value inside your SCP to know where to go in coming back from a subroutine. Okay, again, your subroutine in the assembly language of the 8086, 8088 processor is called a procedure, and its mnemonic code, okay, is PROC. and each procedure is giving some name. And the procedure could be a near if you're calling within the currently active code memory segment, or a far if you go between code memory segments. And each procedure should be ended with end P to indicate to the compiler that this is the end of your subroutine or procedure. Example. You're calling a subroutine by providing a 16-bit operand, which means this is a near procedure. You have only to modify your IP. So you have to replace whatever value inside your IP by this value, but because this is a subroutine, it's a procedure, you have to store the current value of your IP into the stack. Before execution, this is your CS, which stays as is, and this is your new IP. After execution, your CS is as is, while your IP now is modified to the value given in the instructions, which is 1002 hexadecimal. You see here your stack pointer has been displaced 2 locations down to store all the value of your IP in. Okay, good. Another example, return. In returning, you don't have any operand, so you would have to resume back to retrieve back your all the value of IP. So before execution, these are the values of your CS. This is IP, and this is SCP. Return will go first to the stack, get 16 bits from the stack, so the SCP has to go back to the original value for Fs, and your IP should resume the old value of 0003. Okay, this is now your new IP, and this is your new SCP, sorry, and this is your new IP. Good. Here, return with an operand, return 4. This means you go to your SCP, right, and add to it 4 to get the new address from which you retrieve 16 bits to modify your IP. Okay, it adds this 4 to the value inside your SP before removing an IP from the stack. All right, example 3. This now is an instruction which does what? There is, I would say, some subroutine or procedure named compute, and we need to place the effective address of the first instruction in this compute in SI. So this is what this instruction does. It saves the beginning effective address of a procedure called the compute inside your SI. Then you're calling the address SI. So this code will takes you at the first instruction of your compute. of your procedure named compute. So now you are at the first instruction of compute. You start executing whatever code inside your compute. Then this compute is a near. Okay, so these are the instructions below call. But when you call SI, you go to this subroutine called compute, which is a near procedure, which means it is written within the currently active code memory segment. Okay, but we needed the value inside dx. This is an important value for you. You pushed it into the stack and you moved the value of ax into dx now, but the old value of your dx is placed in the stack. Okay, you're trying to get some data from outside port, a port named data. You're getting 16 bits from this port called data inside your system by storing the value inside your AX. So we are reading 16 bits from a port named data. Good. So this read 16 bits is now being sent back to some other port named port. So we're reading through a port named data. We're sending the same reading outside the system through a port named port. All right, now we're done. We're getting back the value of dx. Okay, and we're placing back the value of dx inside ax, and we're retrieving the value of dx from your stack. Then you return back without any operand, meaning you will have to go to the instruction right after the call and resume your execution. Okay, then you end your procedure. So what this compute does is it looks like a transceiver. It receives 16 bits from a port named data, and it sends these very same 16 bits outside the system through a port called port. So it's a transceiver, receives and sends and transmits some data.